We can take a question while. Oh, yeah. She's already set up. Okay, there we go. Yeah, so our next speaker is Xiaoming Mao from Michigan, and she's going to talk about geometric frustration and the pathways to complexity in self-assembly.
So there's a laser pointer over here. Let's see if this one works. I'll proceed with this one and the laser.
Okay.
Okay, yeah, good morning, everyone. It is a great pleasure to be here. I'd like to thank the organizers for giving me the opportunity. So today I'm going to talk about our recent work on geometric frustration, self-assembly, and the pathways to complexity. And I'd like to say that please feel free to stop me at any moment if you have questions during the talk. So I'd like to start by showing you some pretty pictures from nature. So what you're looking at here are pictures of coccoliths, which are these little structures you can find at the bottom of the ocean. The scale bar here is about 2 microns. And these are structures made by single-celled algae called Coccolithophorus. They take calcium from the ocean and make these little armors to protect themselves, which are really interesting to look at. You can have regular dodecahedra, you can have minimal surfaces, and you can have this interesting structural hierarchy. So the chemical component here is calcium carbonate, which we may think to be a boring material. We use that to make chalk to write on blackboard. However, in the hand of biology, they can take so many different intricate forms. Of course, these are not singular examples of complex structures. In biology, we have many more examples. For example, our hair and our bones, which at the macro scale appear somewhat boring, but as you zoom into their microstructures, from the molecular scale all the way up to the macroscopic scale, you have several hierarchy of complex chiral organizations. So why do these structures have to be so complicated? They are not disordered and they are not ordered either. They have very complex symmetries. What is their purpose in biology, and can we make these structures in the lab? So these are all big questions that are kind of intriguing to think about. Before that, I would like to first talk about a more basic question. What do we mean by structural disorder? What do we mean when we say the structure of one material is more complicated than the structure of another material? So how do we think about that? It is clear to us that there are 2 simple limits, right, when we talk about the structures of matter. In one limit, you have ordered structures like crystals, and in another limit, you have complete, uncorrelated, boring disorder, such as atomic gases. If you try to measure the complexity of these materials using simple measures such as information entropy, you may say that this limit is much more complicated than this limit, because in order to completely reproduce a structure like this, you need to store all of the information. Right? However, although there's a lot of detailed macroscopic information, not all of the information is useful. It is often possible to write simple, effective theories to describe materials like this, and we do not need all of the information. Right? However, in between order and disorder, we know that there are systems and materials that are truly complicated, and you cannot use a simple, effective theory to describe them, and these pictures speak for themselves. So to capture this notion called effective complexity has been proposed. And one of the first places it appears is in this book by Murray Gell-Mann, and it also relates to many other earlier concepts such as Kolmogorov entropy, etc. So basically, it captures the non-random information in a system and describes the true effective complexity. And it has been argued that in between order and disorder, we can have this so-called Goldilocks zone, where effective complexity peaks, and the system has the best efficiency, robustness, adaptability, and multifunctionality. And it's also been argued that our Earth is running at this Goldilocks zone when we look at all kinds of biological problems. So these are very interesting notions, right? So for us as physicists, I think one interesting question to think about is basically, can we assemble these complex structures in the lab, for example, using inorganic nanoparticles without the biology? So the examples I show here are from evolution. It takes billions of years to arrive there, but we can think in terms of engineering materials. Can we make materials so that they can assemble themselves like this, and as a result, serve some functionalities? Another way to ask the question is, are these complex structures hard-coded from the biology, or it is possible to have some simple instructions and the physics, chemistry, and the geometry can do the job and give us these materials? So how do we think about that? Let's again start from these simple limits and think about what actually exists in between. So we have the limit of order and disorder. There are many pathways we can go in between. It is not a simple one-dimensional line between order and disorder. Right? One obvious pathway in physics we all know about is to introduce little bits of disorder into an ordered crystal. You can have defects, grain boundaries, you can have polycrystals, and eventually you have disordered materials. There is, of course, also the pathway going out of equilibrium. You can have interesting pattern formation problems that go between order and disorder. And of course, there is also the pathway of biology. The pathway I would like to talk about today is a somewhat less discussed pathway between order and disorder. And I would like to argue that geometric frustration can serve as a continuous tuning node that help us tune the system between order and disorder and explore the proliferation of complexity between order and disorder. So how does this work? When you talk about geometric frustration in a physics audience, this is the picture that usually people would think of. You can have antiferromagnetic interactions on a lattice where each of the face has odd numbers of edges around them. So as a result, this spin doesn't know what to do. That's a geometric frustration. The geometric frustration I want to talk about here is a different type. It's sort of a more simpler kind of pure geometric frustration, which is just the geometric frustration of packing shapes. So here I'm showing you 5 regular convex polyhedra in 3 dimensions. There are only 5 types of convex regular polyhedra. So can we pack 3-dimensional Euclidean space we live in using these shapes? This is an interesting mathematical problem. It is known that only the cubes can do that. You can have a cubic lattice where you have 100% volume fraction, no overlap, no gaps, and you have long-range order. For all of the other shapes, they are geometrically frustrated, and you cannot have a perfect crystal in Euclidean 3D space with no gaps or overlaps. So how do we think about that? Let's take tetrahedra as an example. Here, by looking at the dihedral angle of a tetrahedra, it is clear that you can see you can pack 5 of them around one edge. You almost close a ring, but then there is a small gap because the dihedral angle is slightly smaller than 2 pi over 5. You can take 20 of them, almost getting an icosahedron, but again, you have small gaps. So this is the type of geometric frustration we are talking about here. Of course, this is no new concept in condensed matter physics. This geometric frustration has showed up in many interesting problems. For example, theories for glass transitions and liquid crystal blue phases. In this case, it is known that the packing of spheres in 3-dimensional space is geometrically frustrated, very similar to the packing of these polyhedra. And using that, very interesting theories have been proposed to understand the glass transition. This also showed up in the context of self-assembly. There has been interesting models describing frustrated self-assemblies of nanoscale or colloidal scale components when, for example, the fibers want to twist relative to one another, or some polygons have shape mismatch, and you get interesting complex branching structures. So what we would like to discuss here is the new question of how geometric frustration related to complexity. So we talk about the structural complexity of materials. Can we relate that to geometric frustration, or can we use geometric frustration as a control variable to study complex structures? So how do we think about that? So here I would like to quote an interesting recent paper where the authors try to study physical foundation of biological complexity. And this is a figure they showed where this axis is complexity of interactions and this axis is level of organization. they argue that one origin of complexity in biology is from frustrated molecular interactions. You have attractions and repulsions, and they mismatch from one another, and that over the length scales cause complex phenomena, striped glass-like spaces, self-organized criticality, and eventually to the complex macroscopic biological world. So again, from a physics point of view, we can start from here and think about what happens when we take these frustrated molecules in the lab. What do we get? Right, so typically, either we cool down slowly, the system finds a long-range order, you get a crystal, or you cool down quickly, you get a glassy-like system. Why can't we get the interesting stuff in the middle if we try to mimic what happened in these biological problems? So to be fair, I should list that in the inorganic world, there are complex structures, right? So for example, we all know that snowflakes can take many interesting shapes. And there's also diffusion limited aggregation, give you fractals and sometimes multifractals. There is a lot of complexity there too. However, one thing we are interested in is to think about the role of geometric frustration as controlling these generation of complex structures. For these examples I show here, snowflakes and diffusion limited aggregation, they occur in out-of-equilibrium conditions. You have to have particular kinetic conditions in order for the complex structures to form. However, when you have geometric frustration, that fundamentally obstruct the formation of long-range order. Can we make use of that to make the formation of complex structures more inevitable and programmable? This is what I would like to discuss here. So this leads to the outline of my talk, and I'd like to acknowledge my collaborators. So the first work I would like to discuss is frustrated self-assembly of non-Euclidean crystals of tetrahedral nanoparticles. This is done in collaboration with my former postdoc, Francesco Serafin, my colleague Nick Kotoff, and his postdoc, Jun Lu, and my colleague Kai Sang. And then after that, if I have more time, I will talk about the two new recent projects on frustrated assembly of hyperbolic crystals and rationalizing Euclidean self-assembly using these non-Euclidean crystals. Yes.
Sorry, one question. So
Yes.
what about initial conditions? Because that can control how complexity grows.
Yes. So here, so far we solved the problems we solved are simple minimizations. So we cut a part of the non-Euclidean crystal, and which part to cut depend on the initial condition, right? So we have not touched that complex problem. It is very important if you consider the whole out of equilibrium condition for how they form. Any other questions before I proceed? Okay, yeah, and these two are done in collaboration with my student Nan Cheng and my colleague Sharon Gosser and her postdoc Philip. Okay, so let's start from the first one, and I'd like to start from an experiment from Nick Kotoff's lab. They take semiconductor nanoparticles, in this case cadmium telluride. The surface of these nanoparticles are coated with chiral ligands that can form coordination bonds. And they take these nanoparticles in a solvent and let them assemble. And after some time, they get very interesting shapes like this, these twisted assemblies. And in different conditions of the same system, they can also get all kinds of interesting geometries like twisted bundles and achiral bundles. And in other similar types of nanoparticle plus ligand systems, they also get all kinds of complicated shapes showing up. So when we first look at these experiments, what really strikes us as physicists is really how do you get all of these complex shapes where the building blocks are just a simple polyhedron? Where is the complexity from? So to see that, let's look in a little more detail in the geometry.
So it gets all these shapes, so it's not universal then, like what, I mean, is it all starting conditions or that determine the various shapes?
So that's a very good question. So these experiments are actually very repeatable, but you get different shapes in different solvent conditions. You can tune the solvent so that mostly controls the attraction and repulsion between the particles, and you can get different structures. So they have phase diagrams. Okay. So let's look at the geometry of putting these particles together, right? So as we mentioned, the tetrahedra is geometrically frustrated. And when you have these particles try to assemble to one another, the ligands make them bind face to face. And when you try to just put them together like playing toys, right, bind them face to face, you can get 1D chains without frustration. And there are two chiral versions, left-handed and right-handed tetrahelices. But when you try to put these tetrahelices
Can actually
together,
control, are these ligands uniformly distributed on the faces, or do they know that these ligands are fairly uniformly distributed along the
it
faces?
is pretty uniformly distributed. So there is a subtlety that the ligands are chiral.
Right, and I saw you wrote that, and
Yes.
what does that?
So that is one of the things I did not have time to get into. That causes, so when the particles bind, that causes a rotation between the phases. That selects the chirality of the final product. Yeah, so that's an important point. Yeah. So when you try to bundle these tetrahelices, they can't go together because of the geometric frustration. However, it is an interesting mathematical fact that they are frustrated because we live in Euclidean space. If you have curvature in three-dimensional space, you can actually close the gaps. You can have a perfect crystal of tetrahedra. You just need some curvature. So how do we think about that? It's quite abstract to think about having curvature in three-dimensional space. And so let's start from a simple two-dimensional example, where imagine you have pentagons and you try to tile a plane with pentagons. We all know it can't work because the interior angle is smaller than 2 pi over 3, but bigger than 2 pi over 4, so it can't work. However, you can introduce a little bit of curvature and sorry, I have to click a button to make it work. So, okay, now I think there is a delay or something, but imagine in your brain that you can fold this together and you can get a dodecahedra, right? Dodecahedra is like taking 5 pentagons and fold them together by introducing a positive Gaussian curvature in 2D. You can close the gaps and you get a perfect crystal. Okay? And here we call it a crystal in the sense that the local environment of every node is the same, of every edge is the same, of every face is the same. It's a finite system, but we could call it a crystal in this sense. It's perfectly ordered. And here we get a dodecahedron, and all of the nodes live on the surface of a two-sphere, which is the surface, all of the nodes live on a two-sphere, which is the surface of a ball in 3 dimensions. Okay, so that is what happens in 2D. And then in 3D, it's very similar actually. We can take the dodecahedron we got from the last step and try to think about how they pack in 3-dimensional space. There is a geometric frustration because the dihedral angle is slightly smaller than 2 pi over 3. You put them together, there are gaps. Okay, this video is important to play. So you can make a 1D chains of these dodecahedra with no frustration. However, when you try to put the chains together, there are gaps. Interestingly, you can take 2 of such pillars, each has 60 dodecahedra, and put them next to each other and introduce a little bit of positive curvature. The role of the positive curvature is that it closes the gaps between these dodecahedra, and at the same time, because it's isotropic, it also closes the rings to themselves. In the end, you get a solid 3-dimensional structure that is the so-called 120 cell. It is an example of so-called regular polytope. So polytope is a generalization of polyhedra to higher dimensions. All of the nodes now live on a 3-sphere, which is the surface of a ball in 4 dimensions. This picture looks distorted, right? Some of the dodecahedron is bigger, some are smaller, but in the actual crystal, in the actual 120 cell, they are all the same. It is a perfect crystal in this sense. Okay? We are looking at a projection from 4 dimensions to 3 dimensions, so they look distorted. Is that clear? Yes.
So in your 3D picture, is there any distinction between these polytopes having curvature versus swelling? And it seems like they have these gaps and then they kind of swell to kind of close up together and be confluent.
Yeah, so at a small scale, locally, you could swell and fill the gaps, but at a larger scale, that accumulates a stress that grows as a power law from the center. So you cannot solve the problem by just making everybody bigger.
Okay.
Any other questions? Okay, so the video I showed is the example of 120 cell made of dodecahedron, but the packing of tetrahedron, which is the particle we talk about here, is very similar. I just don't have a video online on that. What you get is a so-called 600 cell. It is also a structure featuring positive curvature. It is actually due to 120 cell. They have all the same symmetries. So these are well-studied problems in mathematics, right? So why do we think that they are relevant for the experiment we're looking at here? Our argument is that these non-Euclidean crystals represent the true thermodynamic ground state for these particles in terms of their interactions. Because when you have such perfect crystals, it's 100% volume fraction. You have long-range order, and you have perfect face-to-face attachment. It is clearly the lowest point of the potential energy of their interactions. So it is the true ground state. And to demonstrate the thermodynamic relevance of such a ground state, I would like to quote an old Monte Carlo study from the 1980s, where the author studied Monte Carlo simulation of sphere packing on a three sphere. So you have positive curvature in the three-dimensional space, and you try to see what a sphere packing does in this curved space. So the perfect structure using this logic, what you should get is the so-called 120 cell, because each sphere will occupy the space of a dodecahedron, like you saw in the video. And indeed, when you run the simulation on the three sphere with the correct density of particles, the system really quickly condenses into the ground state of the 120 cell. In contrast, if you run such simulations in flat Euclidean three-dimensional space, many of us have the example that it takes forever to get an FCC crystal, right? Because it is frustrated and you always have geometric defects. So this is a demonstration that this is a frustrated tessellation, and this is a happy, perfect ground state. It's a very wide minimum in the free energy landscape. So in this case, we get completely different crystals in the curved space and the flat space. And then the new question we are interested in studying here is that, can we actually observe these non-Euclidean crystals in our space? We can't have the whole thing because it's going to be terribly stressed, but can we have pieces of non-Euclidean crystal in Euclidean space self-assembly problems? So that leads to what the work I would like to present here. And here I will ignore a lot of details and just summarize what we did using a simple diagram. So this is a simple summary of the analytic theory presented in this paper here. Basically, we start from some polyhedra packing rules where we say we want to have a certain number of polyhedra and close the gap, and we can get precisely what curvature we need to do that. And then we can find the non-Euclidean crystal. From here, we have the symmetries of the problem, and there are well-developed mathematical tools to generate a crystal according to some packing rules. And then we take these non-Euclidean crystals and use that as a basis to write a continuum theory. Basically, it gives us a non-Euclidean metric, and we can use that to write an energy that includes all kinds of interactions in the problem. And the core of such an interaction energy is what we call elastic energy, that features the deviation of the metric of the assembly problem from the ideal metric. So the ideal metric has a non-Euclidean curvature, which cannot be compatible with Euclidean three-dimensional space. So this term is never zero, but we want to minimize it. Okay, and there are also other interactions in the problem. So then, using this continuum theory, we can also use that as a guidance to cut a part of the non-Euclidean crystal. As we mentioned, we can't have the whole thing because it's too stressed, but we can cut a sheet out of the non-Euclidean crystal. In this case, we study the 600 cell and we take 2 layers of the 600 cell, which has low surface energy. And then by doing energy minimization, we can use that to, from a minimization calculation, we can find the morphology. And in this case, the morphology we find is helicoid, where these particles can assemble into a helicoid-like shape that minimize the sum of these different types of interactions. Okay, so the essence here is that we start from a geometrically frustrated assembly problems and find the minimal energy state. That state is always pre-stressed because you cannot reach the non-Euclidean crystal. Okay, so here we can make predictions and compare to experiment. We are still at the very early stage of actually making this a predictive theory. Basically, a simple prediction we can make is, for example, the pitch of this helicoid as a function of the interaction between the particles, basically depending on the elasticity parameter and the electrostatic repulsion between the nanoparticles. And we can compare to experiment. In the experiment, they can change the solvent properties and they get this assembly at a different pitch. And we get a qualitative agreement with the trend, where when you have more or less electrostatic repulsion, the pitch of the assembled helicoid changes. And currently we are collaborating with Sharon Glotzer's group to run molecular dynamic simulations to see how these particles actually find each other to form such a non-Euclidean crystal. This is one example of the snapshot. This is a really interesting structure to look at. It's perfectly ordered. There's no defect or anything. And yet it is stressed. So it has no stress along this direction. But as you go out in the width direction of the ribbon, it splits because this is a crystal in non-Euclidean space, not in our space. Okay. So that is the first part of the work. Any questions on that? Yes.
So the amount of frustration should set a length scale of the final object that you can build, right?
Yes. Yes, I'm trying to go back to that equation. Yes, that is this R here. This is the radius of curvature of the 600 cell. But in order to actually connect it to the experiment, which is extremely complicated, we have to renormalize this length. So basically, as you can see the scale bar here, the particles are nanometers, but the structures here are microns. So it's really not as simple as this. Instead, we have many layers and there are disclinations. So a simple way to think about it is that you should renormalize this length, but that controls the
Yes.
Yeah, can you say something about your remarkable term G minus G bar squared dV? I mean,
Yes.
when you start thinking about it, the mind boggles. How do you actually represent? How do you represent that? You have dV, for example, is written in flat space, I guess, right?
No, so dV, I ignored a lot of details.
Yeah.
We take the non-Euclidean space metric
Yes.
and we assign a coordinate system according to the tetrahedral particles. So we have a coordinate system in the curved space.
In the curved space.
Yeah. So this dV is from the coordinate system in the curved space.
And what is G then?
So G is a metric. So yeah, it is this G mu nu. So I have a metric tensor for the non-Euclidean crystal, which takes a form like this. It's actually not that complicated, right? So I have one direction that is perpendicular to the other two, but the other two directions rotate relative to one another as I go across the perpendicular direction.
So that's G bar. What's G then?
Yes, G is what we need to solve in the minimization problem.
Which is in real,
G is the real metric.
the coordinates of physical vertices
Yes.
in actual space.
Yes.
Somehow projected into the curved space.
Yes, so this is the curved space, and this is the actual flat space metric that we are going to solve in the minimization.
Yeah, but the measure is curved, right?
Yes,
The
that's the
dB.
question, yes.
So that's the question, you're doing a flat space with a curved measure.
But there is
So the G bar, there's no problem, it's a curved metric, and
Yes.
the measure is curved, the dB.
Yeah.
But G, the blue one, is flat, so, but the measure is still curved in curved space, or am I?
Yes, the measure is still in curved space because we're describing the problem as energy assigned to the particles. If the particles are perfectly ordered in the non-Euclidean crystal, the measure should be the non-Euclidean measure.
Maybe later. you can
Yeah,
discuss it,
I think I can see the problem you're pointing out, but we can describe that later.
It's really understanding, yeah.
I'm trying to, I guess I don't understand fully like what this non-Euclidean crystal like physically represents.
Yeah.
What does it, like what are we concretely talking about when we're talking about a non-Euclidean crystal?
So it is a crystal that by introducing curvature, so I think the easiest way is still to think about the tessellations. So
So it's a crystal that could tessellate a non-Euclidean space?
yes,
And you're looking for the metric of that non-Euclidean space that this crystal tessellates?
yes,
Okay,
that's right.
okay.
Okay,
So can I ask something about going back to your beginning
Yeah.
slide about complexity?
Yeah.
Actually, I think what you showed is entropy, right? And complexity goes up and then down generally because
Yes.
in the disordered state, you know everything again. So even though it has high entropy, it has no complexity.
Yeah.
So in the intermediate state, where things are most interesting, which is what you have, can you sort of quantify then the complexity?
yeah. So we're looking into that a lot recently. So there has been many quantitative measures of complexity that has been proposed in the literature, right? So basically, a lot of them start from the Shannon entropy, but the Shannon entropy doesn't completely capture the problem, right?
Not
You
even
have to
approximately, right?
distinguish the useful information and the useless information.
Yeah, right.
And this is very complicated. And so my opinion is that it often depends on the context. In different contexts, this could be useful or not useful.
Right, but you have something very specific here with your
So
frustration.
you mean you have some kind of prior in the measure of
Yes.
the distribution?
So probably there doesn't exist a universal measure of complexity across all different problems.
Okay.
Okay, so I think I have
12 minutes. Yeah.
Okay, I'll speed up. So I think we got through the main content. So there are just two new projects I would like to mention a little bit along this line. The first one is about basically what about other polyhedra, right? We just looked at one example. And what's particularly interesting is that for the 5 regular convex polyhedra in 3-dimensional space, for most of them, depending on how you set the packing rule, you can either pack them on the 3-sphere or in hyperbolic 3D space. Say for the tetrahedra, if you force 6 of them around an edge, you need a negative curvature to spread them, so they can either be S3 or H3. And for all of them that can pack in S3, it's the same type of theorem. You just have different amount of curvature. But what about a hyperbolic space? Hyperbolic space is actually significantly more complicated. And to study that, we choose one example that is icosahedra. So icosahedra is more special that the dihedral angle is so large, you cannot pack it on a 3-sphere. Even if you have 3 of them next to each other, they already start to overlap, so it can only pack in H3. And by introducing negative curvature, you can get the so-called 353 regular timing, which is a hyperbolic crystal. Hyperbolic crystals are infinitely large, and it has very complicated symmetry properties. Can you still hear me?
Yes.
Yeah, so what I show here is a so-called Poincare ball projection that shows an infinite crystal in a unit sphere. So the icosahedron in the middle looks big. It is just the projection is distorted. Here, it becomes smaller on the edges, but the actual hyperbolic crystal, you have infinitely many icosahedron. They are all of the same size and packed according to the same rules everywhere. Okay. So anyway, we can run the same recipe of taking such a hyperbolic crystal, cut a part of it, and find the continuum theory that has the correct metric, and use that to project and minimize energy in Euclidean space. So what do we find? So what shows up here is an interesting symmetry breaking problem. So when you have one sheet of icosahedron, it wants to grow bigger as you go from the center of the sheet to the edges. So if you have a small sheet, it can handle such a growth in a way without breaking rotational symmetry. But when it's bigger, the system wants to minimize the stretching energy by curling up like this. So you have to break symmetry. So we predicted such a structure of icosahedron assembly. It's not being observed yet, but it's also, so far this is just a prediction. So this is the first work. And the second new project that I'd like to mention is with Sharon Glosser's group, where we try to think about using these non-Euclidean crystals. Can we learn something about Euclidean space self-assembly, especially condensed phases, which means we look at extended crystals or extended amorphous phases instead of the small classes we've been talking about. So how do the three-sphere tessellations, which are static perfect crystals, related to the Euclidean space thermodynamic self-assembly problem? So in order to do that, we tried to run Monte Carlo simulations of hard particles in non-Euclidean space. This is very non-trivial to do, but Philip worked very hard to develop new Monte Carlo simulations that can take care of that. So what we did was to sweep the parameter of the curvature. So we make a three-sphere that become bigger and bigger, and we add more particles to the system so that we maintain the same volume fraction. And then we observe the assembled structures in the Monte Carlo simulation by looking at it in terms of the Steinhard order parameter. So interestingly, we observed two different types of behavior. The first type represented by dodecahedra. Remember, dodecahedra makes a 120 cell in the non-Euclidean crystal. So here in the Steinhard order parameter space, the non-Euclidean crystal, perfect crystal is here. And as you run Monte Carlo simulation in the three-sphere with different radius, you see that for a small three-sphere, the system just spreads out in this direction. In fact, what happens as you look into the Monte Carlo simulation is that the system adopts more and more disclinations into the perfect 120 cell to relieve the stress. And then you get two types of sites of the original crystal and the disclination site. And as you decurve the system to go to bigger and bigger three-sphere, you see that this cloud of Monte Carlo simulation local environments of the particles move more and more away and eventually merge into the Euclidean crystal at the same density, which is a so-called beta manganese structure, which has two Wyckoff sites. And that, in this case, we see that there is a continuous evolution from the non-Euclidean crystal to the Euclidean crystal. We can use the non-Euclidean crystal to rationalize what we observed in Euclidean 3D space. But that's not always the case. We also see different cases where they are completely unrelated. You just jump to a different crystal. That is represented by octahedra, where the perfect crystal is the 24 cell. But as you run simulation at bigger and bigger three spheres, it just becomes disconnected with the original non-Euclidean crystal. The system just figured out that there is a much better ground state, which is the rhombohedral crystal. Okay, so this is, yes?
I'm not familiar with the term tessellations in this context. Could you give us a definition of that?
Right. So there is a distinction between tessellation and assembly. Tessellation means non-thermal. So at least in the context we are working on, tessellation means non-thermal. You just consider the mathematical problem of packing them together. And a perfect tessellation is partition space into these little units that is your particle. And assembly is the thermodynamic problem.
Thank you.
Okay, so this is the second, I think I'm almost done. So coming back to the topic of complexity, right? So we talked about a few examples of using geometric frustration to look at self-assembly problems. Somewhat, the mathematics is somewhat complicated, but we have not really touched the core of complexity yet. So this is because we are just starting to look at this problem. We have taken the simplest route of starting from polyhedra, non-Euclidean crystal, to predicting the morphology basically by minimization. But there are many steps we can get a very interesting complexity, which we have not done yet. It's a future study. For example, the packing rule can be very complex. You can have different types of non-Euclidean crystals, which is fortunately a well-documented problem. And there is the statistical mechanics we have not touched much yet. We've only been looking for the ground state. When you put together thermal fluctuations and non-Euclidean geometry, a lot of interesting things can happen. And also, when you cut a domain, we don't have to cut a trivial sheet. It can be all kinds of geometric shapes, and we hope to recover some interesting geometries that has been observed in natural systems. So basically, we would like to argue that there is an interesting non-Euclidean design space that we can use to study self-assembly problems. So with that, I would like to thank the funding sources and thank all of you for your attention.
Thank you. We have time for questions, more questions. Yes.
So the same idea of going to higher dimensions was also used in jamming, as you know, yet. So I wonder if you could calculate why this seems to be so powerful to go to high dimensional jam states and project them, and then go to high dimensional crystals, go down. I don't understand. There must be some relationship between why this works the same, but I have not. I don't understand it at all.
Yeah, that's a very interesting question. I think there are different ways to go to higher dimensions, right? In the jamming problem, it is in higher dimension, essentially you have a mean field theory, right? And in other contexts, people also go to higher dimensions, for example, to describe quasicrystals. Quasicrystals can be seen as cut a high-dimensional crystal. Here, you need a high-dimensional space. However, the system occupies only a 3D portion of that high-dimensional space.
Yeah, like the hyperuniformity stuff that Sal was doing, and this stuff is very similar in spirit.
Yeah.
Yeah.
So there are interesting relations between these different cases. You go to high-dimensional space in different ways.
So, I mean, another way people suggested was to measure the Kolmogorov complexity of your coarse grain description.
Yes.
Have you thought about applying that kind of idea? Because you have the coarse grain description here, right?
The coarse, you mean the continuum theory?
Yeah, but at the intermediate scale, not the microscopic degrees of freedom. You can do that for cellular automata, for example, things like that.
Yeah, that is very interesting. So quantitatively measure Kolmogorov entropy, I suppose you have to find some algorithm to generate the structure, right?
Well, you
and
have that.
Oh yeah, that's a good point. We have not thought about that.
Yeah, there's a paper by
interesting.
Scott Aronson and company on this.
Okay.
Yeah.
Yeah.
Sean Carroll and Scott Aronson. Yes.
Nobody has a question. I have a question. So going back to your first part, there's this question about the length scale, and you had an R, right?
Oh, that's a pitch formula, right?
Yeah.
I have to go back to the list of slides. Just 1 second, let me find that slide I will reshare.
Maybe you can repeat the question.
Yeah, so the question was that, so you say you renormalize that R if you want to get certain shape. I mean, can you get some of the shapes by renormalizing? That's question one. Second is, how do you renormalize this R?
Yeah, these are very good questions. So in this case, since we do not have fluctuations, right? So when I talk about a renormalized R, it is just a simple way to say that we can add disclinations that change the curvature. Right? It's not the actual RG type of renormalization. But from another perspective, I think when you consider the actual thermodynamic problem, there is a renormalization of the curvature of the space. I think probably that will be very interesting, and that may lead to different phases.
questions from students? Okay, thanks very much, Xiaoming. Very nice.
I'm glad that we're recording. There'll be a lot of people listening.
Recording work, you know?
Yeah, you're only managing to stay this morning. Sorry? You're only managing to stay this morning, or you'll come back and test?
Have to say.
Yeah. I know, it's so much different.